elsewhere. Beyond swaps, how working memory combines gist and item information.
Okay, let's imagine that you're walking in a garden and you see this beautiful pond full of water lilies. Then you meet your friends and try to describe this wonderful thing to them. Here, you might start by recalling a group of yellow water lilies, then the pink one, the red one, and so on. And as we know that our working memory has limited capacity, and we couldn't possibly memorize the scenes in full detail, we try to exploit the fact that this world is full of statistical regularity or patterns, so we can compress similar information together as a chunk. And in doing so, we could improve working memory performance. As you can see, a participant could recall memory from the top display, which contain multiple similar stimuli with lower error compared to the bottom one. However, compression comes with a cost. From the scene here, you can see that there are different shades of red water lilies. But when we group them together, the colors are remembered to be more similar to each other than they really are. And we lost some specific detail of that item. So in order to compress objects together, attraction bias toward the gist or representative of that group is introduced into the memory. For example, if we look at the circle located in the black square here, when participants were asked to report the size of this circle, it is memorized as bigger than the real size when it is grouped with the big blue circle, and smaller than the real size when it is grouped with the red small circle. So now we are wondering whether compression provides enough benefit compared with the cost of increasing memory bias. For example, when you're asked to remember these 4 circles, you can see that most of them are in yellow-green color range, while there's one of them that has blue-green color. And now I ask you to recall the color of that one. Even though you remember that the color is probably in blue-green range, but there's a noise or uncertainty of what the true color really is. And as you know that most colors are within blue-green coloring, then it might be reasonable to minimize overall memory error by combining these two information together. So it looks like there may be some benefit when combining these two representations together, but when should we rely on more on the gist and rely more on using only item-based memory? And to address this gap, we developed a model which could be implemented as a summation between gist and item-based representation. And first, we start with creating a representation of memory by using a target confusability competition model, or TCC. To explain the model briefly, when we try to remember the green circle here, there will be an increasing activity of neurons which respond to that certain color. But not only neurons specific to that color will fire, but also neurons which respond to similar colors such as yellow-green here will fire too, but with lower firing rate depending on the similarity of color to that target color. And during the maintenance period, when we try to hold that item in all memories, a noise will increase and could introduce the memory error. In this model, the color that participant report will be the one which generates maximum signal after adding the noise into the activation function. Here you can see that instead of recalling the two colors, we recall the blue-green one and resulting in memory error. Now we got the representation of individual memory. How could we get the gist level representation? Okay, let's start with the typical working memory task here, but instead of asking for each item color, I will asking for the gist or the average color of all items. And as we use the TCC model here, each item in this display will create an activation of different groups of neurons depending on the colors. And here there's a recent study proposed that the gist representation could be derived by a perceptual summation of each item activation function. And in doing so, that model could explain many findings in ensemble perception. And after we get the representation of both gist and item-based memories, the gist bias model is the weighted summation between two of them. And you can see that after the combination, the gist bias model has a higher peak than the individual model, but still lower than the gist model. And furthermore, you can see that it also shows the asymmetric signal intensity with a strong signal toward the gist in this one. Okay, and to see how this model works, let's start with the first example. As you can see here, all three stimuli are very similar to each other and have a small similar range. And if we choose the left item as target, Now we get its TC function. And then we can get the TC function of the GIST level representation by summing our item TC function together. And you can see that as like ultimately a very similar, and we get a strong GIST representation. And if we simply ignore the GIST and only use item-based representation, we'll get the typical error distribution in working memory tasks that look like symmetrical and there's no bias. Now, what will happen is we combine these two representations together, just like what you see in the orange one here. Here we get a symmetric error distribution. You can see that there are more proportion of error toward the GIST in this orange distribution compared to the one that didn't combine the GIST. And more importantly, you can see that the error distribution after combining these two representations become narrower. This one reflecting the precision bias trade-off in this case. And here's another example. You can see that compared to the previous one, these stimuli are more dissimilar to each other and they have a larger stimulus range. And if we choose the right one as a target and combine them with the GIST using the same ways as the previous one, now we see that combining these two representations for this target only increase bias, but not the precision in this case. And from these two examples, we can formulate the prediction from this model. When the stimuli are highly similar, the GIST representation will become stronger, make it more beneficial to combine these two together. And this will result in more precise but also more biased memory. On the other hand, when the stimuli are highly dissimilar, it will be suboptimal to combine these two representations together. So we will get a larger error and weaker bias for the GIST in this one. Then we will look at the simulation of model. This one is a root mean square error from of the memory. And the y-axis here represents root mean square error, and the x-axis here represents a similar range. So the low range here means that the stimuli are very similar to each other, and the high range is like when are like very different from each other. And each line here represents a different memory strength or D prime. So the high D prime values mean that memory is strong and less likely to be corrupted by noise. As you can see here, the dark line with high D prime has lower error compared to the yellow one which has lower D prime. And now we plot every line for our D prime values here. Overall, we can see that as limit range increase, there's an increasing in memory error for our D prime values. And for the bias symmet range relationship, the positive value here means that there's an attraction bias over the GIST, and the higher the value, the stronger the bias is. And here we kind of got a non-monotonous relationship. For the smaller symmet range, we can see that the bias gradually increase and reach the plateau. And for the larger symmet range, you can see that the bias decrease for all D prime values. And to see whether the model prediction is accurate, we look at the data from previous study. In this experiment, there are 4 triangles with different orientation presented on the screen, and there are 3 subtasks that participants need to perform. The first one is they will either remember one item, all 4 of them, or report the GIST or the mean of that 4 items. And in this experiment, there is a range manipulation from 30 degrees, 60 degrees, and 120 degrees. And here's the result from set-4 condition. You can see that when the range increase, there's an increase in memory error and decrease in memory bias. Now we put the simulation from the model and the real data together. We can see that the model captures this error and range relationship very well. And here the model also captures this range and bias relationship quite well too. And finally, to see how well the model could fit the data quantitatively, we fit 3 different models to the data. The first one is the GIST-only model, which assumes that the individual memory is completely replaced by the GIST. Next, we have the GIST bias model. And finally, the individual-only model, which assumes that we only use item-based representation, but not the GIST. And to see how well the model fits the data, we calculate BSE for each of them. The low BSE value here means that the model fits the data well. Here we plot BSE as a difference between each model BSE to the GIST bias model. So if the difference is higher than 0, it means that those models fit the data worse than the GIST bias model. And when the difference is lower than 0, then it means that they fit the data better than the GIST bias model. And from the result here, we can see that the gist bias model significantly outperforms other two models. And we found that the average gist weight is around 0.48 and is significantly higher than 0, showing that participants did combine gist and individual level representation together. And here, if we use the gist weight from the data to generate simulated error distribution for each range, like I showed you here, then we compare this simulated error distribution to the real one from experiment 1. We can see that the model could capture this asymmetric distribution toward the gist pretty well. And to conclude our findings, this gist bias model could capture this asymmetric error distribution found in the data. It also predicts the relationship between symmetric range to memory error and bias. And lastly, the model outperformed both gist-only and individual-only model, showing that it could fit the experimental finding well both quantitatively and qualitatively. Overall, the results suggest that what we see as a compression might not be simply a replacement of individual memory by the gist memory, but rather an adaptive combination between the two of them. And furthermore, this model provides a way to test further hypotheses about such as how the gist weight might adaptively change depending on the strength of the gist level representation. Okay, and before ending this talk, I would like to thank everyone from CCN and Brady for